Welcome back, guys. Today we're going to finish up our visual organization section in sensation and perception. Here are your ideas before we get started today. How do we use binocular and monocular cues to perceive the world in 3 dimensions and perceive motion? So we left off yesterday with depth perception and this idea of a visual cliff, and you watched at the very end of yesterday this experiment, and so we're going to pick up right there. From the 2-dimensional images falling on our retinas, we somehow organize 3-dimensional perceptions. Depth perception enables us to estimate an object's distance from us. At a glance, we can estimate the distance of an oncoming car or the height of a house. Depth perception is partly innate, as Eleanor Gibson and Richard Walk in 1960 discovered using a model of a cliff with a drop-off area, which was covered by sturdy glass. Gibson's inspiration for these visual cliff experiments occurred while she was picnicking on the rim of the Grand Canyon. She wondered, would a toddler peering over the rim perceive the dangerous drop-off and draw back? So back in their Cornell University laboratory, Gibson and Walk placed 6 to 14-month-old infants on the edge of a safe canyon and had the infants' mothers coax them, as you saw yesterday. Most of the infants refused to do it, indicating that they could perceive depth. Had they learned to perceive depth? Learning seems to be part of the answer because crawling, no matter when it begins, seems to increase an infant's wariness of heights. Yet, the researchers observed that mobile newborn animals come prepared to perceive depth, even those with virtually no visual experience, including young kittens, a day-old goat, newly hatched chicks, all of which we talked about yesterday, and they would not venture across the visual cliff. Thus, it seemed that biology predisposes us to be wary of heights, and experience amplifies that fear. So how do we perceive depth? How do we transform 2 different 2-dimensional, 2D retinal images into single 3-dimensional 3D perception? Our brain constructs these perceptions using information supplied by one or both eyes, which brings us to this. So try this. With both eyes open, hold 2 pens or pencils in front of you and touch their tips together. Now do so with one eye closed. With one eye, the task becomes noticeably more difficult, demonstrating the importance of binocular cues in judging the distance of nearby objects. 2 eyes are better than 1. Because your eyes are about 2.5 inches apart, your retinas receive slightly different images of the world. By comparing these 2 images, your brain can judge how close an object is to you. The greater the retinal disparity, which is the difference between the 2 images, the closer the object. So try it. Hold your 2 index fingers with the tips about 1/2 inch apart directly in front of your nose, and your retinas will receive quite different views. If you close one eye in front of your nose, and your retinas will receive quite different views. If you close one eye and then the other, you can see a noticeable difference. You can also create a finger sausage, as in the figure that you're looking at. At a greater distance, say when you hold your fingers at arm's length, the disparity is going to be much smaller. We could easily build this feature into our video computer systems. Movie makers can simulate or exaggerate retinal disparity by filming a scene with 2 cameras placed a few inches apart. Viewers can wear glasses that allow the left eye to see only the images from the left camera and the right eye to only see images from the right camera, and the resulting 3D effect, as 3D movie fans know, mimics or exaggerates normal retinal disparity. Similarly, twin cameras in airplanes can take photos of terrain for integration into 3D maps. Monocular cues. So how do we judge whether a person is 10 or 100 meters away? Retinal disparity won't help us here, because there won't be much difference between the images cast on our right and left retinas. At such distances, we depend upon monocular cues, depth cues available to each eye separately. So monocular cues can include things like interposition, linear perspective. These things can be available to either eye alone. Here are some examples. motion perception. Okay, I'm going to go back and forth just a little bit here. So first we're going to talk about relative height, and I think that I added, relative height, a little bit about this image right here. We perceive objects higher in our field of vision as farther away because we assume the lower part of figure ground illustration is closer. We perceive it as a figure. Invert this illustration and the black will become the ground like a night sky. Next, relative size. This image right here. If we assume two objects are similar in size, most people perceive the one that casts the smaller retinal image as further away. Depth perception. Interposition. Interposition is this image right over here is the example. Interpose means to come between. If one object partially blocks our view of another, we perceive it as closer. So obviously our brain perceives this deer as closer than that one. Linear perspective, that one's probably pretty obvious. That's this image right here. Parallel lines appear to meet in the distance. The sharper the angle of convergence, the greater the perceived difference. This is also called, if you remember your old world history and art history, that this is vanishing point and perspective and definitely the illusion that allows for that creation. Relative motion. Relative motion, you guys have all experienced, kind of being messed around with when you're sitting next to a train or something. You can't tell if you're the one. It feels like you're moving when you're not moving. You've all experienced this before. So as we move, objects that are actually stable may appear to move. If while riding on a bus you fix your gaze on some point, say a house, for example, the objects beyond the fixation point might appear to move with you. Objects in front of the point will appear to move backward even. The farther an object is from the fixation point, the faster it will seem to move, which can mess with your brain. Okay, and last but not least, light and shadow. So in art history, we call this chiaroscuro, but for our purposes, shading produces a sense of depth consistent with our assumption that light comes from above. If you invert this illustration, the hollow will become a hill. Okay. So all of these allow also for depth perception and visual organization. We just talked about these things. Go. And moving on. Motion perception. Imagine that you could perceive the world as having color, form, and depth, but that you could not see motion. Not only would you be unable to bike or drive, you would have trouble riding, eating, or even walking. So normally your brain computes motion based partly on its assumption that shrinking objects are retreating, not getting smaller, and enlarging objects are approaching. But you are imperfect at motion perception. Large objects, such as trains, appear to move more slowly than smaller objects, such as cars, moving at the very same speed. Perhaps in an airport you've noticed that jumbo jets seem to land more slowly than little jets. To catch a fly ball, a softball, you want to achieve a collision with the ball that's flying your way. To accomplish that, people follow an unconscious rule, one they can't explain but that they know intuitively. Run to keep the ball at a constantly increasing angle of gaze. So a dog catching a frisbee does the same. The brain also perceives continuous movement in a rapid series of slightly varying images, a phenomena called stroboscopic movement. As film animation artists know well, you can create this illusion by flashing 24 still pictures a second. The motion we then see in popular action adventures is not in the film, which merely presents a super-fast slideshow. We construct the motion in our heads, just as we construct movement in blinking marquees and holiday lights. When two adjacent stationary lights blink on and off in quick succession, we perceive a single light moving back and forth between them. Lighted signs exploit this phi phenomenon, it's called, with a succession of lights that creates the impression of a moving arrow. Perceptual constancy. How do perceptual constancies help us organize our sensations into meaningful perceptions? So far we have noted that our video computer systems must perceive objects as we do, as having a distinct form, a location, and perhaps even motion. Its next task is to recognize objects without being deceived by changes in their color, their brightness, their shape, or size, or top-down processes called perceptual constancy. So regardless of the viewing angle, the distance, the illumination, we can identify people and things in less time than it takes to draw a breath, a feat that would be a monumental challenge for even advanced computers, and that has intrigued researchers for decades. Color and brightness constancies. So color doesn't actually reside in an object. Our experience of color depends on the object's context. If you view an isolated tomato through a paper tube, its color would seem to change as the light, and thus the wavelengths reflected from its surface changed. But if you viewed that tomato as one item in a bowl of fresh fruit and vegetables, its color would remain roughly constant as the lighting shifts. This perception of consistent color is known as color constancy. Though we take color constancy for granted, this ability is truly really remarkable. A blue poker chip under indoor lighting reflects wavelengths that match those reflected by sunlit gold chips. Yet bring a bluebird indoors and it won't look like a goldfinch. The color is not in the bird's feathers. You and I see color thanks to our brain's computations of light reflected by an object relative to the object surrounding it, but only if we grew up with normal light, it seems. Monkeys raised under restricted range of wavelengths later have greater difficulty recognizing the same color when illumination varies. Figure 19.6, which is the one that you're looking at right here, dramatically illustrates the ability of a blue object to appear very different in three different contexts, yet we have no trouble seeing these disks as blue. Similarly, brightness constancy, also called lightness constancy, depends on context. We perceive an object as having a constant brightness even while its illumination varies. This perception of constancy depends on relative luminance, the amount of light an object reflects relative to its surroundings. White paper reflects 90% of the light falling on it, black paper only 10%. Although a black paper viewed in sunlight may reflect 100 times more light than does white paper viewed indoors, it will still look black. But if you view sunlit black paper through a narrow tube so nothing else is visible, it might look gray, because in bright sunshine it reflects a fair amount of light. View it without the tube and again it will be black, because it reflects much less light than the objects around it. This principle that we perceive objects not in isolation, but in their environmental context, matters to artists, interior decorators, and clothing designers. Our perception of color and brightness of a wall or a streak of paint on a canvas is determined not just by the paint in the can, but by the surrounding colors. Comparisons govern our perceptions. You guys are going to have to read a bit about the color and brightness constancies because I'm going to peek out on my time here. So why don't you read color and brightness constancies in your on your own, and then I'll pick up with visual interpretation and be done for the day.